lecture today on high frequency response of small signal amplifiers. So far we have only talked about mid-band frequency response, in which we ignored all capacitors. We ignored the coupling and bypass capacitors. We assumed them to be infinitely large, and we also ignored C pi, the base to emitter junction capacitance. We ignored C mu, the collector to base junction capacitance, and we ignored C0, which is across the output, that is collector to emitter, which mostly consists of stray capacitance and load capacitance. In mid band we assumed this to tend to 0, so that all capacitor effects were neglected. Now we consider the effect of these capacitors in two steps. One is, we first consider the high frequency response, in which these are the capacitors which will show their teeth, and these capacitors, coupling and bypass capacitors, are large enough so that at high frequencies they act as short. So for high frequencies we still assume that the coupling and bypass capacitors have negligible effect, that is, they act as short circuits. We consider the transistor internal capacitances and the load capacitance and the stray capacitance across the load. In the process we bring in the concept of a decibel, which I am sure you have been introduced to, but it is usual to express gain in terms of decibels, and if it is power gain, then power gain ratio is P out divided by P in, and what we do in decibels is we take the log of this and multiply by 10, so many dB, D small, B capital. Okay, many people make this mistake. Capital B stands for Bell, B-E-L-L, Alexander Graham Bell, and D is deci, centimilli in the same sense. Okay, so this B should be written with a capital B, okay, because it is the first letter of a proper name. And if it is voltage gain, on the other hand, also expressed in decibels, then since power is proportional to voltage squared, this would be multiplied by 20 log 10 V out by V in, or if it is current gain V in, yes, if it is current gain, then instead of V out by V in, it would be I out by I in. That is it, that is the difference. And the major advantage of the decibel scale is compression, range compression. You see, if V out by V in is 10, then the value is 20 dB. If V out by V in is 100, that is 1 decade higher, then the value is simply 40 dB. So what is 10 times gets reduced to only twice. On the other hand, if this is 1000, V out by V in is 1000, then it is simply 60 dB, okay, multiplication by 3. So it is a range compression, and most of the frequency response plots that we make, if we take the ordinary ratio, then we require a large sized graph paper, and also it may not be possible to accommodate all the complete range of gain, similarly the complete range of frequency. So we plot on a log scale, and the idea is again a compression. Okay.
So in this decimal case, this ratio is the phasor ratio?
This ratio is the magnitude ratio. Okay, that's a good question, good question. The gain that we express here is usually the magnitude ratio, not a phasor. Decibel with a phasor ratio doesn't mean anything. Okay, decibel is always with reference to the magnitude. Okay, before we take up the actual high frequency response, we also like to recall a few simple facts from circuit theory. If you have an RC network like this, and if there is an input here and an output here, V in and V out, then the transfer function of this circuit is simply given by 1 by 1 plus j omega RC for sinusoidal excitation, which I can write as 1 plus j omega by omega 0. Alright, and if I take the magnitude, this is simply 1 by square root of 1 plus omega by omega 0 squared, and the angle of H is minus tan inverse omega RC. It is important to recall this, because I am not going to derive this every time. Whenever such a network occurs, we will simply recall what it is. And the input impedance Z of j omega is simply R plus 1 over j omega C, which I can write as R 1 minus j omega 0 divided by omega. Is that clear? Why it is so? If I take R common, then j omega CR, which is omega by omega 0, and 1 by j comes as minus j. Okay. If I plot H of j omega, magnitude versus omega, then it starts from 1 when omega equal to 0, and then it goes down like this. Okay. At omega equal to omega 0, the value is 1 by root 2 or 0.707, and in terms of decibels, if this is taken as 0 dB in the dB scale, if this is taken as 0 dB, then naturally this corresponds to minus 3 dB, not 3, minus 3 dB, okay, because the ratio is less than 1, 0.707, and therefore omega 0 is called the 3 dB cutoff frequency, 3 dB cutoff frequency, or simply cutoff frequency. Okay, omega 0 is called the 3 dB cutoff or simply the cutoff frequency. One more fact which shall occur again and again is, if I have a resistance and a capacitance in parallel, then the equivalent impedance is R divided by 1 plus j omega CR. This also we shall get again and again, and we will not do this calculation again and again. Obviously, this circuit, the series R and C circuit, acts as a low pass filter circuit. That is, it favors low frequencies and it discriminates against high frequencies. So it is a low pass filter. On the other hand, if the capacitance and resistance are interchanged, that is, if we have a C in series and an R in parallel, then you can show that this is a high pass filter and the response is like this. At infinite frequencies, the value is 1, this is magnitude H of j omega. At infinite frequencies, the value is 1, and at omega 0, once again omega 0 is equal to 1 over RC, the value is 0.707, okay, or 1 by root 2, and in terms of decibels, again this is 0 dB, this level corresponds to minus 3 dB, and omega 0 is again called the 3 dB cutoff. This is a high pass filter because above omega 0 frequencies are favored, below omega 0 frequencies are not favored, they are discriminated against, and therefore omega 0 is kind of borderline, artificially defined 0.707. There is no reason why you could not define 0.5 level as the cutoff frequency, but this is artificially defined. 3 dB is a very nice figure, and that's why we always concentrate on 3 dB cutoff. This is a high pass filter. As far as the phase is concerned, the phase would be tan inverse, yes, 1 by omega CR. The phase would be tan inverse 1 by omega CR. No negative sign. Negative sign comes in the low pass filter because the voltage output lags the input voltage. Here the output voltage leads the input voltage. Okay. Now, if I take the take the BJT, the bipolar junction transistor, emitter, collector and base, then all that is needed to take care of high frequency response is to include C pi, C mu and C0. So, the hybrid pi equivalent circuit would be Rx, then instead of R pi we have a C pi and an R pi. This voltage is V pi, okay. This is the internal base B prime, external base B, this is the emitter circuit, emitter terminal E, and then because we are now including C mu and we are considering high frequencies, the reactance of C mu usually shall be much smaller compared to R mu. Okay. You remember at mid band C mu was considered open and therefore R mu had come into the picture. In some cases we considered, wherever inconvenient we discarded it. Here it is extremely inconvenient to include R mu, and the logic for ignoring is not inconvenience, it is that R mu usually is large compared to the reactance of the capacitor. So, we do not include R mu. Is the point clear? We do not include R mu. And then we have the GM V pi in parallel with R0 and C0. This is the other capacitance that has to be taken into account. So, this is the collector, this is the emitter. This is the hybrid pi equivalent circuit. Before we incorporate this in a common emitter amplifier, let us consider the definition of two relevant quantities. One is called the beta cutoff frequency, F beta, beta cutoff frequency, and the other is called Ft or transition frequency for the BJT, for the device. Let us see what these quantities are. Usually manufacturer specifications, manufacturers specify either F beta or Ft or both. Okay. Let us see what these quantities are. Suppose we have a common emitter circuit driven by a current generator, IS, driven by a current generator. We are drawing only the AC equivalent circuit. We are not drawing the biasing resistors or anything. We are drawing only the AC operation. And suppose we short circuit the collector and let the current that flows be I0. Okay. We consider this very simple circuit. We have biased this properly, and then as far as AC is concerned, we have short circuited the load. The load is short circuit. Maybe we have connected a large capacitor, okay, and we want to measure the current in this short circuit. The input is a current generator, that is, it is a voltage generator with infinite impedance, or a current generator, its shunt impedance is infinity. Okay. Now, if I draw the equivalent circuit, AC equivalent circuit, what we have is I sub S, then it is very convenient to ignore Rx. So, we ignore Rx. Okay. We ignore Rx, wherever necessary we shall include it, but at the present time it does not add much. So, and it is in series with a current generator, isn't that right? Even if Rx was there, it does not have any effect, because internal impedance of a current generator is infinity, and Rx plus infinity is also equal to infinity. So, it really does not matter. C pi R pi, then we have C mu and GM V pi, then we have this parallel combination of R0 C0, but this is short circuited and this is I0. So, as far, and this voltage is V pi, of course, V pi. as far as R0 and C0 are concerned, they are ineffective because they are shorted. Okay, they are ineffective. Therefore, I0 would be equal to, this short circuit current would be equal to GM V pi plus, okay, now the current through C mu, let us call this I mu, this will be minus I mu, agreed? At this node, I0 should be equal to GM V pi minus I mu. And what is I mu? I mu is what is the potential of this point? 0, because it is short circuited. So the current I mu should be simply equal to j omega C mu V pi. Now usually this current can be ignored because C mu in any case is a small capacitor as compared to GM V pi, and therefore we write first approximation I0 is approximately equal to GM V pi. We ignored I mu. Pardon me?
Why do you ignore I mu?
Why do I ignore? Because I mu is usually very small quantity as compared to GM V pi, as we shall see in examples. We will validate this later, but we can ignore this. And as far as V pi is concerned, in order to calculate the current gain I0 by Is, as far as V pi is concerned, V pi is Is flows through a parallel combination of R pi, C pi and C mu, because C mu also comes in parallel with this. Okay, so Is V pi would be equal to Is multiplied by the effective impedance. Effective impedance would be, it is a parallel RC combination, so it would be R pi divided by, yes, 1 plus j omega R pi multiplied by C pi plus C mu, absolutely correct. And therefore I0 by Is would be equal to, if you substitute V pi here, you get GM R pi, which we shall call beta 0. Beta 0 is equal to GM times R pi divided by 1 plus j omega multiplied by this quantity. This quantity we call as 1 by omega beta. That is, omega beta is equal to 1 over R pi C pi plus C mu. Okay. What is the significance of this expression? Look at this expression. Let us call I0 by Is as beta of j omega, because beta is now, this ratio is now a function of frequency. This ratio is a function of frequency. This is equal to beta 0 divided by 1 plus j omega by omega beta. Don't you see that this is exactly similar to the expression for transfer function of a low pass filter? That's why I did that earlier. And you notice that the short circuit current ratio, this is the definition of beta. But now because of C pi and C mu, beta depends on frequency. And you see that if omega equal to 0 at DC or at frequencies much less compared to omega beta, if omega is much less compared to omega beta, then beta is equal to beta 0. That holds up to about mid-band. Up to about mid-band, beta is approximately equal to beta 0, and then when you exceed the mid-band, when you go to higher frequencies, omega beta, omega by omega beta, this factor produces a reduction, and the ratio and the plot of beta j omega magnitude versus omega naturally would be of the same form as that of a low pass filter, and the value at 0 frequencies beta 0 and the value at omega beta would be equal to beta 0 divided by root 2. So omega beta is a cutoff frequency. Omega beta is the frequency. Pardon me?
Okay, magnitude.
Yeah, magnitude beta 0 by root 2. Omega beta is the frequency at which beta comes down from its DC value by 3 decibels. Agreed? If we take dB value here and here, the difference will be 3 decibels. Okay, so omega beta is a 3 dB cutoff, but because it applies to beta, we call it omega beta as the beta cutoff frequency. Beta cutoff frequency, and beta cutoff frequency can be expressed either in radians per second or in hertz. In hertz, f beta would be equal to omega beta by 2 pi. So it would be 1 by 2 pi r pi c pi plus c mu. Agreed? This is the beta cutoff frequency. Another frequency that is defined with reference to the same curve is the frequency at which beta reaches the value 1. Obviously, if the short circuit current amplification factor is less than 1, that is, that frequency is beyond this, obviously the transistor shall not be useful. Okay, there is no current amplification. In a common emitter circuit, if there is no current amplification, well, the transistor is useless. And therefore, this frequency is absolutely the highest frequency up to which you can use the transistor for amplification. And this frequency is therefore defines a transition between usefulness and uselessness. And therefore, this is called a transition frequency, omega t. A frequency at which the magnitude of beta reduces to unity. Now let us see what this frequency is. You see, the magnitude is beta 0 1 plus omega by omega beta whole square, and this is required to be equal to 1 at the frequency omega equal to omega t. At the frequency omega t, the value becomes 1. So if I simplify this, I get beta 0 squared minus 1 equal to omega t by omega beta whole squared. All right, as compared to beta 0 squared, this 1 is negligible, and therefore omega t is equal to beta 0 multiplied by omega beta. And if you see the expression for beta 0 is gm r pi, and omega beta is 1 by r pi c pi plus c mu, and therefore this is simply equal to gm divided by c pi plus c mu. This is absolutely dependent on the transistor parameters gm, c pi and c mu, and is the frequency above which you cannot use the transistor gainfully. You cannot gain anything by using the transistor. No current gain, and therefore it is a useless quantity. Omega t is called the transition frequency, and you notice that the frequency in hertz shall be gm divided by 2 pi c pi plus c mu, and this would be equal to beta 0 times f beta. Okay, typical value is 300 megahertz. Typical value of ft is 300 megahertz, and if beta is equal to 100, then f beta is typically how much? If ft is 300 megahertz and beta is 100, 3 megahertz. Okay, these are typical values. F beta is typically 3 megahertz, ft is typically 300 megahertz. Okay, that that completes the preliminaries. The other thing that we have to notice is that instead of a BJT, if we use an FET of any kind, it doesn't matter what it is, we again have to take care of 3 capacitors. One is the one is CGS, and this voltage is VGS, the phasor value, and then we have to take care of the gate to drain. So we have a capacitor CGD, this is the drain. From the drain you have the GM VGS, there is no resistance here, no resistance here, because gate to source and gate to drain, they are either reverse bias junctions or metal oxide semiconductor capacitor. Okay? So GM VGS, and then you have the inevitable dynamic resistance of the drain RD, and perhaps a output capacitance C0, which is basically stray, but it also contains a small amount of capacitance contributed by the device. So we will keep it C0. C0 usually is a very low valued quantity. You must also recognize that CGS, CGD, C pi, C mu, C0, they are of the order of pops, picofarads, 10 to the minus 12. For example, a typical value of CGS and CGD would be 2 picofarads. Typical value of C pi would be 10 picofarads. Typical value of C0 would be about 5 picofarads. But nevertheless, even though these are very small quantities, they cause disaster at high frequencies, as you shall see. Yes.
So isn't there a capacitor between drain and source?
Is there a capacitor between drain and source? If you recall, it's a channel. It's an N channel, and there is ohmic contact here, ohmic contact here. So if at all there is a resistance, not a capacitor. This is not a, there is conduction, there is no depletion. Capacitance require a separation of charge, there is no separation of charge. Okay? So there is no capacitance between the drain and the source. If there is, it will be taken care of by C0. If at all there is, if at all due to a peculiar combination of voltages there is a depletion, or due to the defect in a substrate there is a depletion, it can be taken care of by C0. Now let us go back to a BJT common emitter amplifier and see how to analyze such an amplifier. Our circuit is the usual circuit. We have R sub C, RE. We assume that this capacitor is infinitely large so that it behaves as a short circuit. Coupling capacitor, we assume this to be infinitely large. This also behaves as a short circuit. This is the load. This voltage is V0 and the current here is I0. The biasing, we assume the usual circuit R1 and R2. And there is a coupling capacitor C1 which we assume to go to infinity, the source resistance and Vs. Usual circuit, okay. This voltage is Vi and this current is I sub I. Once again we are interested in voltage gain, current gain, but the gain that we shall mostly be interested now, which is affected by frequency, which is affected by capacitances, is more than AV, now it is AVS, because most of the sources in practice, whether it's a microphone or a let's say cartridge pickup from a record player or a CD-ROM player, whatever it is, there is an internal resistance, okay, and mostly we shall be concerned with this gain. This gain will be very much affected by the internal capacitances of the transistor. Let us draw the equivalent circuit, then we will see how this is affected. We have Vs, Rs, then we have R sub B, and then Rx, R pi, C pi, this voltage is V pi, okay. We have C mu, For obvious reasons we ignore R mu. Then we have the GM V pi R0, and we shall have RC and RL all in parallel. This voltage is V0 and this voltage, this current is I0. Oh, there is a C naught, yes, okay. There is a C naught, yes. We make some simplifications now. In this circuit, we assume that Rx tends to 0. Rx causes a problem because then if Rx is there, we have to consider this and this as independent nodes. If Rx is not there, we can combine the two. Usually Rx can be ignored. Okay? And you see these three resistances can be combined into one resistance, we call this RL prime. RL prime, we lose I0 thereby, but we can recover it if we know V0, I0 is V0 by RL. Okay. So RL prime is this resistance, and if Rx is ignored, then Rb and R pi can be included in a single resistance capital R pi. We have of course tacitly assumed that C1, C2 and CE, they go to infinity. Okay. With this simplification, our equivalent circuit becomes the following. We have Vs, Rs, and we have R pi. This is the notation we shall be using all through. The voltage across R pi is V pi. There is a C pi. There is a C mu. And there is a GM V pi. The capacitor C0 and the resistance RL prime, the voltage across which is V0. Now you see we have only to write two node equations. One of them is here and the other is here. First, let's consider what happens at the output. Let's write the node equation at the collector node. Then you see the current through RL prime is V0 GL prime. Okay. Current through C0 is J omega C0 V0. Okay. This takes care of the current through this and current through this. Then there is a current GM V pi. Okay. GM V pi. Then plus another current which goes through C mu. Okay. This would be J omega C mu multiplied by V0 minus V pi. But V pi is also the same as Vi. Okay. V pi is the same as Vi. This has been affected by making Rx tend to 0. Okay. Therefore, if you substitute V pi equal to Vi here and write down the voltage gain between output and input Vi, not AVS, this is AV, then you can very simply see that this is given by J omega C mu minus GM divided by GL prime plus J omega C mu plus C0 multiplied by, no, that's all, GL prime. This is 1 by RL prime. GL prime is 1 by RL prime. Is this expression correct?
Sir, what's the first equation equated to? Was it 0?
This is equal to 0. Yes, of course I should have done it. It's a KCL at node C, and therefore this is equal to 0. Alright, is this expression correct?
Yes, sir.
Alright. Now look at how I manipulate this expression. J omega C mu minus Gm divided by Gl prime plus J omega C mu plus C naught. I can write this as minus Gm divided by Gl prime. What shall I get here? 1 minus J omega C mu by Gm divided by 1 plus J omega C mu plus C0 multiplied by RL prime. Right. Okay. I can write this as, what is this quantity? Minus Gm RL prime. This is the mid band voltage gain. So I can write this as AV0 1 minus J omega by some quantity omega 3, where omega 3 is defined as Gm divided by C mu. Gm divided by C mu. Okay. What is Gm divided by C mu? There is a quantity which is akin to this. Gm divided by C pi plus C mu is omega t. This is not quite omega t. Would it be higher than omega t or lower than omega t? Higher than omega t. So this so omega 3 is greater than omega t, and therefore this quantity omega by omega t, omega 3 shall be a negligible quantity in the frequency range of operation. Is the point clear? Omega 3 is greater than omega t, the transition frequency, and we are going to operate the transistor much below the transition frequency, and therefore this quantity omega by omega 3 will be very small compared to unity, and in the numerator I can approximate this by 1. There is a further justification which I shall show you. In the denominator I can write this as 1 plus j omega divided by omega 2, where omega 2 is equal to 1 by C mu plus C0 multiplied by RL prime. Okay. Let us take the example that we have been pursuing so far to get the ratios, to get an idea about omega 3 and omega 2, and the justification that in the numerator I can ignore this term. Let us see what the justification is. Let us take the example that we have been pursuing so far. R1 equal to R2 equal to 220K, RE equal to 1K bypass, RC equal to 2.2K, RL equal to 4.7K, GM with 1 milliampere current is 39 millimole, Rx given 100 ohm, we ignored that, R pi at this current is 2.6K, beta 0 is equal to, now we have to say beta 0 not beta, is 100, product of these two, R0 is 139K, and C mu is 2 puff, C pi is 10 puff, and C0 is 5 puff. These are the various parameters of the circuit and the device which are given. So, the first thing to find out is RL prime, because this occurs in omega 2. RL prime would be R0, that is 139K, parallel RC, which is 2.2K, parallel 4.7K, and this is equal to 1.48K. 1.48K. We have calculated this earlier also. And if I know this, then AV0, why this 0 now? It's a mid-band value. AV0 is minus GM RL prime is equal to minus 39 millimole multiplied by 1.48K and this comes out as minus 57.7, equivalent to how many decibels? How do you calculate that? 20 log 10, not of minus 57.7. It's always the magnitude. Okay, so simply 57.7, and this comes out as 35.2 decibel. Mind you, when I write this number as so many decibels, it cannot be an equal to sign. It is equivalent to. Triple parallel lines means equivalent to. Okay, so minus 57.7 gain is equivalent to 35.2. You have to retain the phase separately. That the phase shift is 180 degree has to be retained separately. Okay, so after this we find out omega 3, which is equal to Gm divided by C mu, that is 39 millimole divided by C mu is 2 puffs, and this you can see is 1950 multiplied by 10 to the 7 radians per second. There is a reason why I have expressed it as 1950. Okay, and omega 2, which is equal to 1 over RL prime, which is 1.48 K multiplied by C pi plus C mu, which is 7 puff, and this calculates out to 9.7 times 10 to the 7 RPS, radians per second. And you notice that omega 2 is much less than omega 3. Okay, omega 2 is much less than omega 3. So the numerator factor can be ignored. If you are not convinced, let us see AV j omega magnitude would be equal to AV0 magnitude multiplied by, in the numerator I shall have 1 plus omega by omega 3 square, and in the denominator I shall have 1 plus omega by omega 2 squared. Okay? If omega is nearly equal to omega 2, is around omega 2, then this factor obviously compares favorably with unity. But when omega is nearly omega 2 by omega 3 square is 9.7 divided by 1950 square, approximately 1 by 195 square, approximately 0.25 times 10 to the minus 4, which is very small compared to unity, and therefore the numerator factor can indeed be ignored. This can be taken as 1, which means that my expression, simplified expression for the voltage gain AV, I can write as AV0 divided by 1 plus j omega by omega 2. And you notice that this again is a low pass expression. It is like the transfer function of a low pass filter, and therefore omega 2 is the 3 dB cutoff frequency for the voltage gain V0 by Vi. It is not Vs, mind you. Vs is a separate story, is a different story. And therefore omega 2, which is equal to 1 by RL prime C0 plus C mu, is the 3 dB cutoff of the voltage gain V0 by Vi. It also shows a simplification in the equivalent circuit. That you remember, in the equivalent circuit there was a C mu which went to B prime, then we had a GMV pi, then RL prime and C0. Okay, I am not drawing the rest of the circuit. This bridge between B prime and collector, which is a feedback bridge between the collector, the output terminal, and the base, which is the input terminal. This effect of this bridge therefore simply amounts to adding a capacitor across C0. Isn't that right? You understand this? No. Okay. If C mu was not there, what would be the cutoff frequency of the output? That would be 1 by RL prime C0. Now the cutoff frequency is RL prime C0 plus C mu, and therefore as far as the output circuit is concerned, what you do is you disconnect this C mu and add a capacitor C mu to C0. I have not said anything about the input circuit, that I am going to look at separately, but as far as the output circuit is concerned, all that is required to take account of C mu is to add a capacitor C0 plus C mu to C0. Is that clear? So output without caring what the input is, the output circuit cutoff frequency can be determined by considering the circuit to be equivalent to this, by ignoring this feedback from collector to the base. Okay. Now let us look at the input circuit. The story is quite different there. You recall the story is that there is a Vs, Rs, then we have R pi, capital R pi, parallel combination of Rb and small r pi, then a C pi, this is V pi, and there is a C mu, then this node voltage is V0. I am not drawing the rest of it. Okay, there is a current generator, there is a whatever it is, it does not matter. But what I am interested in is finding I sub I, this current. Obviously, I sub I shall be equal to V pi multiplied by G pi plus j omega C pi, these two currents, plus V pi minus V0 multiplied by j omega C mu. This current I shall call this as I mu. Okay, this current I shall call as I mu. Now I mu, yes, I mu can be written as V pi j omega C mu, okay, I take V pi common, multiplied by 1 minus V0 divided by V pi, which is equal to V pi multiplied by j omega C mu 1 minus, what is this? V pi is the same as Vi? It is AV. Okay. Now, it would have been very nice if this was a real quantity. Well, what I can write is I sub mu equal to j omega C capital M multiplied by V pi, where Cm is defined as C mu 1 minus A sub V. Okay. If I can define this, if I define this as a capacitor, equivalent capacitor Cm, then Cm shall be given by this. The trouble is that A sub V is no longer a constant. It depends on frequency. And A sub V is a complex quantity. It is AV0 divided by 1 plus j omega by omega 2. And therefore Cm is not a pure capacitor. Cm is a complex, hypothetically defined capacitor. Is that clear? Nevertheless, a gentleman, a very bold gentleman by the name Miller, C.J. Miller, very bold gentleman, he said, we don't care whether it is frequency dependent or not. What we will do is, we will approximate this AV by its mid-band value, AV0. If I do that, AV0 is a real quantity, which means this is equal to C mu 1 plus GM RL prime. This brought revolution in the design and analysis of transistor circuit. It's a revolutionary concept, a very gross approximation, because a frequency dependent function is being approximated by a frequency independent function. Alright. Obviously, this is an approximation, and therefore, this is called Miller approximation.
What is the justification?
This is the justification. There is no more justification than bringing convenience into an engineer's cup. It's simply convenience. He is very bold. He said, let's do this, let's see what happens. Now, to an engineer, and more often than not justifies the means. Do you understand what I mean? The results obtained with this approximation, which is the end product, compare very favorably with exact analysis, and most often, as I said, more often than not justifies the means, and therefore don't ask for any more justification. Only justification is that if you assume this, then the circuit becomes absolutely simplified. Circuit becomes simplified, and the end results, the results that we get from this simplified circuit, compare very favorably with not more than 10% deviation, even in the worst case. And therefore, Miller became a hero overnight. All right? And the circuit, if you notice now, our I sub mu is equal to j omega Cm V pi. Therefore, I sub I becomes V pi G pi plus j omega C pi plus Cm. Is that right? The equation that we have written for the input current I sub I, it simply can be expressed as a product of V pi and a complex admittance, which means that my equivalent circuit now reduces to Rs, Vs, then a capital R pi and a single capacitor is equal to C pi plus Cn. This is sometimes denoted by CT, total capacitor. Total capacitor is the base emitter junction capacitor of the BJT plus the Miller capacitor, and this is why the subscript is capital M, the Miller capacitor. And why does Cm come in? It takes account of C mu. It takes account of the feed forward from the base to the collector through C mu. And we have already seen that as far as the output circuit is concerned, this is V pi. As far as the output circuit is concerned, we have GM V pi in parallel with what? RL prime and C naught plus C mu. This is visible. You see what Miller has done. Miller has decoupled the input and the output, and therefore the analysis of such a circuit can be done by inspection. Nothing else is needed, just your pair of eyes and a little bit of exercise of gray cells in the head, that's all. No node equations, no loop equations, no inversion of matrices. You don't require a computer to feed into the nodes and the parameters and so on. You can just look at it and write down things by inspection, and that's what we will do tomorrow.